So I will speak about the direct product. It has two parts, this talk. The first one, the larger one, is concerned with finite graphs with unique prime factorizations and algorithms to find those prime factors. And the second part is then concerned with some problems that come up when one considers these new classes of graphs with unique prime factorization. So now, what is it all about? The direct product was introduced 1912 by Whitehead and Russell, and then it was studied mainly in algebraic settings. So one of the most important papers or results for this talk are from Tarski and Jonsson from 1953. They did not really publish them. They published them later with a student, with Chang, 1964, and this is in this paper, they showed that products of infinitely many graphs have, under certain condition, the common refinement property. I will later explain that, what it is, but it implies that every finite graph has a unique prime factorization with respect to the direct product. But there were certain conditions, and one didn't know whether they were satisfied, and then it was shown by Mackenzie in 1971. Jonsson was a student of Tarski, and I think Chang was a student of Jonsson and Tarski, and Mackenzie was a student of Jonsson. Yeah? So he wrote a dissertation of about 50 pages in Fundamenta Mathematica, and there he proved that under certain conditions the results of Chang, Jonsson, and Tarski apply. Now these papers, I mean, what Chang had in there, it's all written in the language of category theory and very hard to read. Also the paper of Mackenzie, and of those 50 pages, although only 10 pages really pertain to what is interesting for us, and the other paper not too much, nobody really read it. Yeah? And the funny thing is there are some implications about finite graphs that one could not prove without taking recourse to these papers from 1971 or even 53. And I will talk a little bit about that and say how one can resolve that problem. And also that one can not only prove that the prime factorization is unique, but that one can also find an algorithm. Maybe I should go now to details and to define the direct product. We define the direct product of graphs by considering them as binary relational structures. So when you have a graph, with a vertex set V and an arc set, a set of arcs AG, we write G is VG, that's the vertex set, and RG, this is a relation, and we write U R V if there's an arc from U to V, and we write R V R minus U if for the inverse relation. And now it is clear how this translates from relations to graphs, but it's convenient to do that. And now how is the product defined? Well, if you have two such structures, say G and H, then the direct product is defined on the direct product of the vertex sets. And if you have two vertices, say G and H, and G prime, H prime, then when do you have an arc from G to H? You have an arc when there is an arc from G to G prime and from H to H prime. Now that's very easy. This is the categorical product. By the way, in a way, this is the only product in the category sense. So I will later talk about the Cartesian one, which is not a product in the category sense. Now, how about examples? So on the left, you see a graph, and it is the product of an arc by another arc. So an arc has 2 vertices, the other one also 2, so the product has 4 vertices. And if you look at this edge here in the product, if you project it into the first factor, the projection into the first factor is an edge, and into the other one also. So this is the only pair of vertices in this product that is connected by an arc. Yeah. Now, if you look at the second example, you have in one of the factors you have a loop, and of course you have the following situation. If you take those 2 vertices here, they project into only one vertex, yeah. But this is adjacent to itself because of the loop, yeah. And so you have an edge there. Yeah? Okay, and in the other graph, the third one you have there, the loop gives a loop, and so you end up with this graph on this side here. Okay, now what is this product? What are the properties of that product? This product definitely has a unit. It's the one vertex graph with a loop, and it is associative, and it is also commutative. Now, there are some special cases which have been considered before, and one of them is the direct product of undirected graphs. Now, if this relation is symmetric, that means if you have an arc in one direction and you have it also in the other direction, you can do the following. You can think, okay, if this is always the case, I just replace these 2 arcs by one undirected edge. Yeah? And if you look at the left figure, you see the product of these 2 graphs. And if you do as I said, you get just a direct product as it is usually defined for undirected graphs. Okay, so what is this? So this is already a special case of the direct product of relations as we had before. What do we do for the strong product? We have the same thing as before. Now suppose we have a graph where there's a loop at every vertex. As you have seen before, this means that in this example on the left, you get this graph here, so it's a square with all diagonals, and you have loops everywhere. Now we are a little bit economic, so if we delete all the loops, yeah, we know they are loops, so why should we draw the loops? Then we get the graph on the right side, and this really depicts just the strong product of 2 edges as it is usually defined. Okay, now for these products, the direct product and the strong product of undirected graphs, one can show differently that prime factorization is unique. I did it with Dörfler for the strong product 1970, and one can also find the polynomial algorithms. But if one wants to do that, one uses the Cartesian product. So I will have to, or wish to say a few things about the Cartesian product. Now, everybody, it was mentioned before, but it's convenient to define it again here. And so I do the following. We say the Cartesian product of 2 graphs, G and H, is defined again on the vertex set, which is the Cartesian product of the vertex sets of the factors. And then we have an edge in the product. Say XU is adjacent to YV if either X is adjacent to Y in the first factor and the second components are the same, or if the first components are the same and the second are adjacent in the second factor. So this is an example. This is an example of a product. And what you see is that the product consists of copies of the factors, yeah, of the first factor and of the second factor. And there are no other edges in there, in that product. And it will be convenient to name the copies. So if you have a copy of the first factor that goes through a vertex V, then we denote it by GV. So this would be GV. Yeah? And if we have a copy of the second factor that goes through V, we denote it by HV. So this will be the second one. Why is that important? If we want to see in such a product, every edge is in a copy with respect to a factor. Now, if we want to find prime factors, we can do the following. We take an edge, and then we take all factorizations that exist, yeah, of this original graph, and then, so there will be in every one of those factorizations, there will be a layer that contains this edge, yeah? And then we take the intersection of all those layers. And it is clear that this intersection cannot be a product, yeah? So it must be prime, yeah? Okay, so of course, now the notation I used for this, if I take such an edge is PE, yeah? And of course, if I take another edge, you know, this PF may be the same as PE, that's possible, clearly. But what we can do now is we take just one vertex, we consider all edges that are incident with that vertex, and consider all these PEs, yeah, for these edges that are incident with that vertex. Yeah? Some of them may be identical, so we only use one of them. Yeah? Okay? So we have a vertex and we have edges, yeah, that go out, and they are grouped into edges that are in prime graphs. And then we can take the product of all those prime graphs. And what turns out, it's not hard to show that this really is the original graph. Okay, is it the original graph? No, it is not always the original graph, because you may have, see, I said I would talk about finite graphs, but this also works for infinite graphs, this construction, yeah? And then you may have infinitely many factors, and if you have infinitely many factors and you multiply them together, if they are non-trivial, the product cannot be connected. That's clear, because then you have vertices, you know, that differ in infinitely many components or coordinates, and since every edge is in one of the factors, and so you cannot have a finite path between any of those two vertices, so it's disconnected. Yeah. So the original graph was then a connected component, yeah, of this product. Now, see, this is, and one does call this connected component a weak Cartesian product. Now, the first proofs, I should say that, for the unique factorization with respect to the Cartesian product are due to Sabidusi and Wiesing. So Wiesing 64, Sabidusi 1960. And then, see, I did not say anything about algorithms, and I will not explain how the algorithms are designed, but maybe I should say the first algorithm for the prime factorization of the Cartesian product is due to Feigenbaum, Hirschberger, and Schaefer, 1985. This was later improved and improved and improved, and there's a linear algorithm, linear in the size of the graph. Yeah, you have to consider every edge, so it cannot be better than, in a sense, than OM. Yeah, and this what I published with Istok Petrin 2007. So this is essentially all we need about the Cartesian product. And actually, this is what I had there was more or less proof of the whole thing. Yes. Now, okay. Now, what do we do now with a strong product if we want to factor a graph with respect to the strong product? If you look at that, you see there are edges in there. There are the edges as one would have them in the Cartesian product, and other edges, yeah, non-Cartesian ones. If one can get rid of the non-Cartesian ones, yeah, and then factor the Cartesian stuff, you know, one might be able to get a factorization with respect to the strong product. There's a little catch, because if you look at the other diagram, this one here, you see, well, if I interchange these two vertices, I get an automorphism. And then these edges which are non-Cartesian or not in, which are not in one of the layers, suddenly become edges that are in the layers. Yeah, so they are not uniquely defined here. But if but these two vertices I pointed out, they have the same. They are connected and have the same neighbors. So if there are no such vertices, if the graph, as we say, is thin, then these non-Cartesian edges are uniquely defined. And then one can try to get rid of them. Joe Feigenbaum and Hirschberger and Schaefer, I think, and Schaefer did that with a very smart method, but I will not explain that. I will explain another method, which is due to Richard Hammack. And his idea was the following. So you take one of these products. Take this product, for example. You want to get rid of the edges that are non-Cartesian. Now, if you look at this one here, you have the neighborhood of this vertex with this vertex. Is just this square with the diagonals. Now, if you take the neighborhood of z, then the neighborhood is the whole graph, and the neighborhood of x is this one. Yeah. So the intersection of those two is the neighborhood of x, and the neighborhood of x and of the intersection. The intersection of the closed neighborhood of x with that of y is properly contained in the intersection of the neighborhood of x and the neighborhood of z. Okay, this is this condition. So, and Richard Hammack says this edge is dispensable. And then if you look at this edge, you have the following. You see the neighborhood of x is this here. It's completely contained in the neighborhood of z. And this is also completely and properly contained in the neighborhood of y. So you get that. Yeah. He says, okay, we also don't need this edge. And then, we take a symmetry condition, and we just interchange x and y. And now it turns out, if you delete those edges, you get the so-called Cartesian skeleton. Yeah? The thing is, you may also delete some of the edges that are Cartesian, but that doesn't really matter. The important thing is that you're really left with a graph that is connected. Yeah? And also, if you take the skeleton of the strong product of two graphs, then it is the Cartesian product of the skeletons of the factors. So now, what do you do? If you take a graph G and you factor it, with respect to the strong product, you take all these GI are prime with respect to the strong product. And then you do the skeleton construction, you get this here. You get a Cartesian product. And this SG has a unique factorization as a Cartesian product. These things, it turns out, need not be prime. But it doesn't matter. You really, in some smart way, you can collect some of the prime factors, that will form this one and that one. And altogether, you can prove that the prime factorization is unique. That's another new proof. And you can also use this to find a polynomial algorithm. So I will not do any more details, but just only want to indicate how one does it in one other case. So you take the direct product. If you take the direct product, then you have this strange situation that where we would expect the layers, there may be no edges at all. So what one does there is one takes the square of the graph, which means the Boolean square. One connects any two vertices that are of distance 2 in the original graph by an edge. Say here, Then one removes all loops, and then one has the same conditions one had before. One just replaces the closed neighborhoods by open neighborhoods and has dispensable edges and removes them and gets a prime factorization. Does one? No, not here, because here the skeleton, what that is left, is disconnected. But it's disconnected because here I would only get 3 edges here and here, but nothing in between here. But the reason is that this is bipartite and should not be bipartite. If it's non-bipartite and the skeleton is connected, you can do the same thing as before, get unique prime factorization and get an algorithm. So we have a connectedness condition that's connected and non-bipartite, and the thinness condition, no two vertices have the same neighbors. Then you can do all these things. Now, for the strong product, the first algorithm was due to Feigenbaum and Schaefer, and I extended it into the direct product, but it was essentially their idea. And the idea with the non-algorithmic definition of the skeleton is due to Richard Hammack. We published that together 2009. Now, what is the current situation for these complexities? Just for completeness, I tell you, for the strong product, you have m times the arboricity times the maximum degree. The arboricity is the minimum number of spanning forests you need to span the whole graph, and it is bounded by delta, which is the maximum degree, and by half the minimum degree from below. And for the direct product, you get this complexity. These complexities are not the same as you would find in the book by Richard Hammack and Sandy Krausch and myself, the handbook on product graphs. They are slightly improved, but and will be published soon also. Now, let us go to the directed graphs, yeah? And because all the ideas I mentioned here will be used there, even if I don't do any details. So what one has here is the following. One needs another connectedness condition. This is the one by Mackenzie. We say a graph is R plus and R minus connected if between any two vertices, X and Y, you have a path of this type, an arrow here, and so on. You continue until you get here. This would be an R plus path, and then you also have an R minus path. So this is the connectedness condition, which is needed by Mackenzie. And now, what does that mean, by the way, for undirected graphs? You know, this condition is equivalent to non-bipartiteness in connectedness. Yeah, this is clear. Yeah? Otherwise, it doesn't work. And if you have the strong product and you have loops everywhere, then you just need connectedness. Yeah, so these are just special cases. And what does one do now? Now we have a certain hierarchy. Yeah, so we have this R plus and R minus connectedness. Then we can say, okay, let's just have R plus connectedness or R minus connectedness, or we don't care. It is either an R plus or an R minus path. Yeah. So when we also have some sort of implications. I mean, anything that has this type of connectedness property has this one or that one, and anything that has this or that also has this connectedness property. So this is connectedness. And how about thinness? Well, we say graph is R thin if no two distinct vertices have the same neighbors. Now, we say it is R plus thin if no two vertices have the same out neighbors, R minus thin if no two vertices have the same in neighbors, and we say R prime thin if no two distinct vertices have the same out or in neighbors. And again, you have some sort of hierarchy. Yeah, if this is true, then this here, and that here. And now something nice comes up. If you combine these things, if a graph is R plus and R minus connected and R thin, then you have unique prime factorization, and you have, but this is by Mackenzie, no algorithm yet, yeah? Then if you have that property, if you have this property here, if you have this property here or this property, then you have unique prime factorization and also a polynomial algorithm. And here also, by the way, this relation R is an equivalence relation, R plus and R minus, but this R prime is not an equivalence relation. So what you see is the following. If you have this is a very weak connectedness condition and a strong thinness condition. So if you change that, if you make that a little bit stronger, yeah, this here, yeah, or stronger here, and you relax the thinness condition, so you still get unique prime factorization. I didn't say anything about that. Yeah. Now, how do you prove that? See this. Yeah. See, the first one, part one. This is Mackenzie, Chang, and Johnson and Tarski. Yeah. Now, I will speak about how one can show that. Then that R plus connectedness and R minus connectedness imply unique prime factorization. Was shown actually by 2007 by Glöckler and myself. And the one for R prime, this is new and will be published soon. But I should also say, and here we have skeletons. The proofs are via skeleton constructions. There's another skeleton construction. This is by Mark Helmuth and Thiel and Martz from 2015, and they actually did it for graphs that are reflexive. They have a loop at every vertex and anti-symmetric. Yeah, then they could also do it also with a skeleton construction. Now I can do this here for this part with a combination of these things. The problem is when you have a graph that is R thin and you factor the R classes, you get a graph that is thin. If you have a graph that is not R plus thin and you factor, you get a graph that can be either not R plus thin, not R minus thin, and not R thin. Yeah? And so still, if you do that, if you factor by R plus and then by R and then by R plus and so on and go down, you see you do not really lose any factors, and you can go up again. Then you do the same thing for R minus, going down and going up again. And then you have to realize if you have an R plus class and an R minus class, and the thing is R thin, they can have at most one vertex in common. And using this, one can then show that the prime factorization is unique and also find a polynomial algorithm. But there's no skeleton. So, good. And what can one do with all these things? Sometimes we do something with the distinguishing number, or we can look at the automorphisms and things of that sort, yeah? And the structure of the automorphism group, which was not considered by Mackenzie, etc., is the same as that for the Cartesian product, which I will not write up in detail, but it actually says that the automorphism group of a product of prime graphs is isomorphic to the automorphism group of the direct sum of the prime factors. Yeah, and one can show a lot of things that way. For example, that a graph has a transitive automorphism group if and only if every factor has transitive automorphism group, and many other things. By the way, also graphs that are not thin are thin. You know, they also have unique prime factorization, but not in the R plus case. And the reason is that in the equivalence classes with respect to R, they are complete graphs with loops at every vertex here. And if you factor them, you actually, the prime factorization of such a graph is found by taking the prime factors of n, yeah? And then you get a unique prime factorization. Of course, this does not work in the infinite case, because if you take infinitely many such graphs of K2 with loops everywhere, yeah, and multiply them, say countably many, And take the same thing with triangles. You loops at every vertex, multiply that, yeah. You also get an uncountable graph, or complete graph, you know, with loops at every vertex, yeah. And these are obviously two different prime factorizations. So this does not work in the infinite case, but it does work in the finite case. But anyway, and it does not work in the finite case if you take the R plus classes. So the R plus classes, it's funny, they consist of of several vertices, yeah, that form a complete graph with loops at every vertex, and then there may be some other vertices that are adjacent to all of them, yeah. And this is an R plus class, and you have such, if I introduce a notation, say I call this here 2, 4, here I have a K2 with loops, and it has 4 vertices, yeah? And then it's clear that we have 2, 7, or 6, 7 is isomorphic to this here. These are, of course, prime because they have 7 vertices, so that's easy. And this is the reason why you cannot have unique prime factorization in this case in general. Okay, infinite graphs. So, what does the refinement property say? If you have a product, yeah, of infinitely many graphs, yeah, say B iota, iota in an index set iota, and C kappa, where the kappa are in an index set should be capital K, but I wrote J. Then, and you have another presentation, yeah, okay, you have one presentation with the B iota and the C kappa, and then common refinement means there are structures D iota kappa with the following property, that the B mu are a product of some of them, yeah, and the C kappa are also, a C nu are also a product of some of them, yeah. So, and then you see the original graph is the product of all these structures, the iota kappa. So you kind of refine the presentation. And if you have finite structures, you know, where the number of factors is of course limited, of non-trivial factors is limited, you get, this implies unique prime factorization. And of course it does not imply the existence of prime factorization. And so what can we do now? For example, we can now ask the question, so this here was only true for, we had R plus, R minus connected and thin, yeah? But now the question is, of course, what happens when we have some of the other cases we considered in the finite case. If we have R plus connected and R plus thin, or R minus connected and R minus thin, do we still have a common refinement? Or in the other case that is there, if we have R plus or R minus connected and R thin, do we still have common refinement in that case? And I do think this is true, and it should not be too hard to prove, and it probably you would, but you cannot use the skeleton here, yeah? That's definitely true, because the skeleton, you know, it gives you something with the Cartesian product, but the Cartesian product of infinite graphs is disconnected, so that doesn't work. So you can definitely not do that. But I think you can adapt the original proof of Mackenzie, because what Mackenzie essentially proves is that if you have a subproduct, yeah, and an isomorphism of the graph, then the subproduct is mapped into a subproduct. Or if you have a layer with respect to some factorization and isomorphism of the graph onto itself, this layer is mapped into a subproduct, or maybe a square if you wish. But one just has to be really careful to do that, and it's definitely not easy. Yeah? Now, but this is still not all, because even when you have the direct product, yeah, the product of infinitely many graphs need not be connected. Yeah? So this was not considered by McKenzie. Yeah? And the reason is, of course, the following: if you have a product, yeah, and if you take a path in the product and you project it onto the factors, then this path will be a walk. Yeah. So it will have a length, the same length as the original path. Now, if you take in this product of infinitely many, if the factors, for example, have diameters that are unbounded as such, yeah, so they can all have finite diameters, but for any diameter you should have a factor, yeah. And then I take in the product, I take two vertices such that the distance of the, say, if two vertices, I call them x and y, and that the distance in b iota of x iota y iota is unbounded, yeah, right? So this is what I require. Now, if I had a finite path between x and y, then the projection to the iota factor would have to have distance at most k, but it's unbounded, so this is not possible. Yeah, so this is disconnected. Now what? So what? Well, but then I can ask, similarly to the Cartesian product, where it is known that if you have such a connected graph, then it has a unique prime factorization with respect to the weak Cartesian product. Is this also the case here? Yeah? So if you have a graph which is a component of the direct product of infinitely many graphs, yeah, and you have another presentation of this graph as such a component of a direct product, are these isomorphic? I mean, do we have the same prime factors, yeah, with the same multiplicity? So this is open. This one, but I'm sure one can prove that. But there's even something else. You can also consider a weak product. You take a vertex, and you consider all vertices that differ in the given one only in finitely many coordinates, and then you can look at the graph that is spanned, yeah, by these vertices, yeah. And if you have enough loops, then the thing will have edges in there, will be connected, yeah. So then this it would be called a weak product, yeah. And the question is then, is this representation of a graph as a weak product also unique? Yeah? So we do not know whether we have prime factorization, but when we have, then we would like to know whether this is unique. And is this of any use? Well, for example, I think if you have a product, yeah, and you have the product of infinitely many graphs, it's connected, and if it's vertex transitive, then every factor is connected and vice versa. Yeah? I think this also holds if you have a component of such a thing. But if you have a weak product, then this need not be the case. So for example, Bonato, Hahn, and Tardif showed 209 that if you have such a weak product, which is vertex transitive, then it is possible that all factors are asymmetric. They have no single automorphism. So there are some nice things that come up. So what kind of problems did we have? Let me recapitulate a little bit. Is the presentation of components of connected prime graphs when the product is disconnected unique? Then is the presentation of a connected graph as a weak product of prime graphs unique? Then, now this we would really like to have, but this is not easy, is the criterion for the existence of prime factorizations of infinite graphs. And, I mean, there's some sufficient conditions, of course, yeah, but there is no criterion. Or, for example, we had an example where the prime factorization was not unique, but with the K3s and the K2s, yeah, but this is not thin, yeah. Is there a thin example without prime factorization? And of course, the other problems I had with the R plus and R minus connectedness. And infinitely many problems I left out. And they are the following. What happens when the things are not R plus and R minus connected? What happens? For example, in the finite case, this is, corresponds to the case when you have bipartite graphs. Yeah? And for example, this was mainly studied by Richard Hammack. And for example, he showed that in the finite case, if you have a connected graph which is bipartite, if it does have a it must have a bipartite factor. Yeah, it has a bipartite prime factor also. He showed that this bipartite prime factor is unique. The other factors need not be unique. Yeah? Now, let us just consider this undirected case. What happens in the infinite case? Yeah? Well, there's just one thing that was studied, by chance more or less, and it was Doug Rell and I who did that. You take the infinite hypercube. The infinite hypercube is a weak Cartesian product of K2s, yeah? And this infinite hypercube can also be represented as a direct product of a K2 by some other graphs that are not uniquely defined, yeah? But one can then define and characterize all the graphs that are factors. Yeah, so we have a K2. One can characterize all the other graphs such that K2 by these graphs is a hypercube. So the problem is then, if you have, for example, if you have an infinite graph and you know that K2 is a factor, is this unique? Yeah, means if there is another bipartite factor, must this be isomorphic to K2? And of course, this is only one single problem. It's for undirected graphs, and we did not see what else we had. And here we only have more or less a weak product. There we have, yeah. And what happens if any of the other possibilities occur, which I mentioned, yeah? And this is, of course, all I wanted to say, and I thank you for your attention, and I wish happy birthday to Professor Fiorini.